So this is page 9 in the Unit 1 packet. What we're looking to do is find the derivative of a polar function, but using rectangular differentiation, so dy dx rather than dr d theta. So in order to do that, we want to use the rules that convert us over from polar to parametric, polar to rectangular, I should say. We got an R there, apologies. And so what we're going to do is we're going to differentiate each of these equations with respect to theta or r. It doesn't make a difference. So dx d theta, dy d theta is my choice. But you could do dx dr, dy dr. It's going to work out the same way. All right. So although you'll find that this is going to end lovely. I love it when an app craps out. There we go. So you'll find that differentiating with respect to theta is going to be a little bit more user-friendly. All right, so what I'm going to do is treat this, because it is, as a product of two functions, because r is not always a constant value. You can see in the first example below that r is defined as a function in terms of theta. Right? So when we differentiate, we have to use an implicit approach. The first function, r, times the derivative of the second, which would be negative sine of theta, it's the derivative of this guy, plus the second function, cosine, times the derivative of the first, which is just going to be, well, the derivative of r with respect to theta is dr d theta. All right. Now, when I want to take the derivative of the y equation with respect to theta, same general idea. First times the derivative of the second, all right, that's this guy, plus the second times the derivative of the first, again, another dr d theta. All right, now if I want to find the derivative of y with respect to x, it's actually not too bad because we have all the ingredients here. I'm just going to shrink some things down a little bit to make it fit. We'd be looking at the ratio of dy to d theta, which is the ratio of the two corresponding expressions. Right, and the reason why that's helpful is because if I take dy d theta, and I think I said the ratio of dy to d theta. What I meant to say is dy d theta to dx d theta. The reason why that's a good thing to do is because the d thetas would cancel and you'd be left with just the dy dx. All right, so the right-hand side of that whole equation would just boil down to, I was going to say the simple fraction, but I think we'll all agree there's nothing really simple about this. The fractions, or the fraction. That has all these ingredients. All right, but recognizable ingredients. Because you see in the first example, we have an r. They gave us an r. Very nice of them. We have the means to come up with a dr d theta. Told us 1 plus sine of theta is r. Dr d theta would just be equal to cosine of theta. This is all happening when theta is equal to pi over 3, so I could just pop that in, r of pi over 3. 1 plus sine of pi over 3 is the square root of 3 over 2. Dr d theta, when theta is equal to pi over 3, cosine of pi over 3 is equal to 1/2. So we have those ingredients. We also need to know, I mean, if you're looking around in that model there, you see we have these built-in ingredients, cosine and sine. You have them in a couple of places. So you might as well just crank those out while you're there. Sine of theta. We've already done it, though. Sine of theta, sine of pi over 3 is equal to rad 3 over 2. Cosine of pi over 3 equal to 1/2. All right, so dy dx my r, well, that's just a 1 plus rad 3 over 2. Cosine of theta we just figured out is a half, plus the sine of theta, rad 3 over 2. Dr d theta we figured out was 1/2. It's kind of coming along here. R, again, 1 plus rad 3 over 2. Negative sine of theta, so negative rad 3 over 2. Cosine theta, 1/2. Dr d theta, 1/2. All right. Now, if I want to clean this up, and it's debatable, sometimes you don't need to. Now, they did ask us to write the equation of the tangent line, so we got a little bit more going on here. But this is specifically, I should be specific. Oh, lovely. About my notation, this is when theta is equal to pi over 3. All right. So very important there. What I can do, or one thing I can do, is replace my 1's with 2 over 2's. So I have a nice common denominator across the board. So then I can just wipe out those common denominators. I'll clean it up a little bit first because I don't like to skip too many steps. So we're looking at 2 plus radical 3 over 2 plus radical 3 over 2 over. The second one's a little bit more complicated, but it's not too bad. Negative 2 radical 3 minus 3 over 2. Well, actually, those are going to be over 4. I apologize. We're actually multiplying them. Somebody's screaming at the computer right now. Plus a quarter, which in turn simplifies to 2 plus 2 radical 3 over negative 2 radical 3 minus 2. And those look like they're exact opposites of one another. In fact, if you factor out a negative 1 from the bottom of the fraction here, you have a nice cancellation. I mean, the nicest cancellation. 1 on the bottom, or negative 1 on the bottom, 1 on the top. The slope here would be a negative 1. I mean, that's surprising in how clean that ended up, because it didn't look like it was going to shape up that way. Although we go into these kind of problems with high hopes, it just doesn't always play out. In this case, it did, and our patience was rewarded. All right, so we have that part of it. Now, in order to write the equation of a line, we need more than just the slope. We need either the y-intercept or just a point on the curve itself. The point on the curve, we can actually get that pretty easily, because we have the relationship that we started off with right in the beginning, where the whole journey began. X is equal to r cosine theta and y is equal to r sine of theta. So I could find x where theta is equal to pi over 3. And same thing for y. All right. And so when I do that, I would need r when theta is equal to pi over 3. All right, well, we know that. That's 1 plus the square root of 3 over 2. And we would need cosine of theta. We also know that cosine of pi over 3 is equal to 1/2. We're going to need the same thing for sine to start. But we're also going to need a radical 3 over 2, because that's what the sine of pi over 3 is equal to. All right, so this is all a whole heck of a lot of computational stuff going on here. We can clean it up a little bit further. Multiply through with the 1/2. It's not, and at least it doesn't seem like it's going to clean up quite as nicely as the slope did, but it'll be something. 1/2 plus radical 3 over 4. And then radical 3 over 2 plus 3 over 4. All right. So then we can use our point slope form for a linear function. Y equals m times x minus x sub 1 plus y sub 1. So in this case, y equals -1 x minus 1/2 plus radical 3 over 4 plus radical 3 over 2 plus 3 over 4. Now, if you want to simplify it beyond that, that's up to you, or it's up to me, because that's what I'm going to do now. Just going to make it a little smaller. All right, so I have y is equal to -x plus 1/2 minus radical 3 over 4 plus radical 3 over 2 plus 3/4. All right. Now I can combine some like-ish terms. Let me multiply this one top and bottom by a 2. So we're looking at -3/4 plus 2 radical 3 over 4. So that's going to be positive radical 3 over 4. And then 3/4 plus 1/2. I mean, you can do the math on that if you want to get a common denominator. And it's like 75 cents. You add 50 cents to it. What do you got? $1.25, right? So that's 5/4. And so we have so that's all positive. I got my -x here. That's all equal to y. All right, so after all that work, I definitely want to check to make sure that we didn't botch that up royally. And frankly, I don't want to have botched it up even a little bit, because that was a lot. I got a 1. That's not what I want to do. I certainly don't want to botch it up in the checking process. Yeah, that's the worst. Okay, so I got my limacon, all right? Over whatever interval, it doesn't matter, because I only care about what's happening at pi over 3. But let me graph the linear equation. Y equals -x plus 5/4 plus radical 3 over 4. All right. And the crowd goes wild, except, there's something wrong. So if I don't know why the crowd is going wild. The crowd shouldn't be going wild at all. Crowd should be silent. Stop going wild, crowd. What's wrong with you? I don't want to see any wildness. Now I got to double check. And there it is. Took a second, but when I distributed this becomes negative, this becomes positive. These should have both been positive. Oh boy. All right, so that's a 3 radical 3, if I'm not mistaken, over 4. And hopefully that does the trick. Whew, Hugh Jackman. All right. Well, that's why we check. But anyway, that would be the equation. And that's a nice example of why sometimes it's just not worth it to simplify. All right. But there it is, that's page 9.